All right, let's get an introduction to mechatronics and find out what it is. There are some sample mechatronic systems shown in this slide. The Predator drone is a mechatronic system. My car that I drive, which is a Volkswagen Jetta, has mechatronic components in it. And there's many other examples of mechatronic systems. Why is my car a mechatronic system? Well, there's pieces of it, like I said, that are mechatronic. Even though it's a manual transmission, it turns out that the gas pedal is not directly connected to the engine. Instead, the throttle is connected to the computer, and the computer determines the throttle position. As a matter of fact, I don't drive a gasoline car, I drive a diesel car. It gets about 50 miles per gallon, which is why I still drive it. Anyway, the gas or the diesel pedal, the throttle, like I said, goes to the computer as a requested signal. See, here's the thing. If it didn't work that way, I would be able to mash the pedal and generate plenty of black smoke out the tailpipe, just like the big four-wheeler trucks that are diesel can do. Now, if you think about what that means, that cloud of black coming out of the engine is actually unburnt fuel, so it's inefficiency. It's fuel that went through the engine but didn't help push the car forward. And so what the computer does is it decides, okay, given that the user is pressing the gas pedal or the throttle so far, and we're going this fast, the engine is at a certain RPM, what should the fuel setting be in order to give the user the response they desire from the vehicle? You know, if I push the pedal all the way to the floor, the system will not just inject as much diesel as the pedal would theoretically be calling for. Instead, the computer would ramp it up. It would slowly inject more diesel to get the car to accelerate as fast as possible, but not waste fuel uselessly. Now, why is it mechatronic? Well, we're going to see in a minute all the pieces of a mechatronic system, but this little subsystem in my car actually has the features needed. You see, you need to determine a very precise, well, a fairly accurate measure of the throttle position, but what has to be very precise is the amount of fuel that's injected into the engine. And so the injector pump that was built on these cars is actually a very precise device that actually, unfortunately, costs quite a bit of money to rebuild anytime it's worn out. Anyway, because of the precision of the mechanical system and the fact that we're sensing the user's input here and using an algorithm in a smart device or a computer to actuate then the delivery of fuel to the vehicle, all those pieces together, you'll see in a minute, constitute a mechatronic subsystem for this car. Obviously, the Predator drone is a mechatronic system as well. It has precise mechanical features as well as smart control, and it's not just a pilot sitting there flying it. I guarantee you that these Predator drones have a tremendous number of sensors that also help automate some of the functions and flying of the drone. If not that, at least the weapon systems. There are some older mechatronic systems, things that are no longer popular but were mechatronic systems. If you ever had a VHS player or a beta player, probably not, most of you guys are probably too young to have seen these, but when I was a kid, that's how we watched movies. We didn't have YouTube. We went to the library and borrowed some VHS cassette tapes and went home and watched them. Or we went to Blockbuster when that was a thing and rented some movies to watch. We didn't have Netflix, obviously. But the player itself is a mechatronic system because it had all the components. It was smart. In other words, it basically had a computer that was controlling it. It read sensory input from the system. That's part of the tracking system. And it had precise mechanical features and actuators and things we'll get into more later. Another example was the projectors we used to use here. The projectors, the DLP projectors, actually had an array of tiny mirrors, and the way that array of mirrors worked is it was just you can think of a grid, a very small grid of mirrors, where there were all these tiny mirrors that could be turned electronically, and they could be turned at very high frequency because they're very small. These are MEMS devices, if you know what a MEMS device is. They're made on well, with the same type of processes that computer chips and integrated circuits are made on. So they're very small, they're mechanical, so they actually move, they're very highly polished, so they do behave as mirrors. And each mirror in the array was one pixel on the screen, one picture element, one dot on the screen. What was interesting about this is that the mirrors couldn't determine whether or not red light was reflected off of them. So there's actually a lamp that generated all the colors of the spectrum that were needed. and that lamp shone on or shined onto the DLP, the chip, the array of mirrors, and then the array of mirrors would reflect light as was needed through a color wheel or a color filter as it's shown in this slide. And basically that color filter was always spinning at fairly high RPM, but its position was sensed. So the machine always knew what color filter was in place that the light was going through after bouncing off of the mirrors. And what would happen is, if you know anything about displays, let me back up. If you know anything about displays, you can make any color you want out of red, green, and blue. If you look really close at whatever device you have, whether it's a smartphone screen, a laptop screen, even the old cathode ray tube screens, each picture element is actually made of red, green, and blue. And varying the amounts of red, green, and blue give all the colors you see. So if you turn on red, green, and blue completely, your eye will sense that picture element, that dot, as white. So anyway, this DLP projector had this color wheel that was constantly turning, and say you're in the red section, well, what you would do is you'd set the mirrors so that it's reflecting the correct intensity of red light through that filter, or the red channel through the filter. And as soon as the filter moved where it was in the next section, where there's green or blue, it would change actually the pattern on the DLP mirror section to shine the blue light or green or whatever was needed. And so these mirrors had to change very, very quickly as that color wheel is rotating very fast. And also, you have, say, 30 frames per second. Well, you got 3 colors to deal with. That's 90 different images per second that the mirrors have to align to. So the mirrors were moving back and forth very quickly. Anyway, why is this system mechatronic? Well, I'll show you in just a second. We've talked enough about it. Here's another example of a mechatronic system. It's a laser printer. In a laser printer, there's a mirror that is rotated in order to shine the laser in the at the correct position. Basically, the way it works is the mirror is just constantly rotating, and the computer inside of the laser printer, yes, there's a computer inside the laser printer, that's what controls it, it's trying to print an image, right? And so what it does is it knows where we're at, what line we're on the page, and it knows what the pattern of light and dark should be. Now, as the mirror rotates, basically it gives the printer the opportunity to scan the laser across the page, which then fuses the toner to the page to make the image. So as the mirror rotates, the position of the mirror is precisely measured so that the laser can be pulsed on and off to actually make the individual dots of toner stick to the page across that horizontal line as the page goes by. So this is also a mechatronic system. Here's an image of that engine, if you will. I don't know if my mouse should show up. This section here is the mirror. It doesn't look like it, but these sides are highly polished. Let's see, it looks like there's, 6 sides. The laser is mounted over here, and there's the control board for it. This is actually a motion chip that is involved in controlling the motion of the motor and the mirrors, therefore, and then these two are lenses that focus the laser onto the page, and the page is scanned across here. I don't remember what this part is right here. It's not relevant to our discussion at the moment. All right, obviously, mechatronics is fairly common in industry as well. A robot is actually an example of a mechatronic system. So robots are actually a subset, a certain type of mechatronic system. Of course, they come with their own advantages and challenges, and so there's, the study of robots is a separate topic from mechatronics, but it is related. It's kind of like a child of mechatronics. You probably have never heard of this other industry, but there is a huge industry you may not know about called the converting industry. If you go into a store, say a grocery store, and you start looking around, you might think you see food, but most of the time you don't actually see food. What you see is packaging. All of the packaging has to be made somehow, and the food has to be put into the packaging, there has to be printing, it has to be sealed, and the converting industry is the industry that does this. So converting is also involved in things like magazine printing, newspaper printing, things like that. But the converting industry, even though those two things, print media is going down in popularity because of online media, still the converting industry is a huge industry because packaging hasn't gone away. So anyway, in the converting industry, there's a lot of high-speed processes that have to be accomplished very precisely. And so they are computer controlled. There's a precision mechanical component to most of the machines used in that industry, and those things do qualify typically as mechatronic systems. Here is a mechatronic system I was designing when I worked at Grody. We had some light emitting diodes we were laminating, so it was a very thin sheet that came out, and then when you turn it on, points of light within the sheet would light up. And we needed a way to seal this strip. Basically, the strip was made of a sandwich. There's a lower substrate, the LED die were placed on top of that with hot melt glue, and then a top layer, a clear layer of plastic was put on top. And then the whole sandwich, the thickness was only about 25 to 30, maybe 40 thousandths of an inch thick. Now, being a sandwich, the sides were still exposed to the atmosphere, and so water could actually infiltrate from the sides and cause problems, cause the product to stop working. And that was a big problem. Our products needed to be reliable, and so the machine that I've designed here, obviously this is a left-hand side is a computer rendering or a computer model of it. I was designing it in Pro E, and on the right this is where it was being built. Anyway, the machine was to take in the strip, the sandwich that had already been made, and it was I designed it to lay down a piece of tape that extended past the edges of this thin sandwich, and then it would wrap the edges over the ends. So that it's kind of like, think of taking a regular sandwich you would eat, laying a piece of saran wrap on top of it and just folding it over the edges. That's what this machine did. It had all of the components necessary, although they're not shown here, to qualify it as a mechatronic system. It was a precision mechanical system. It was going to be controlled by a PLC, so it had smart control, and we had to write an algorithm, take sensor input, and control precision mechanical outputs to make this thing work. All right, so what on earth is a mechatronic system, and how do we decide? Well, I think I mentioned the pinball machine earlier that I used in this course. A pinball machine, as it is made, typically, is not a mechatronic system. Well, why not? Mechatronics is mechanical and electrical put together, right? Well, there's a little bit more to it than that. As a matter of fact, this is a graphic that we're going to use quite a lot through this course. It was made by my colleague Henry Zhang on main campus as he and I developed this course, and I really like it. I'm going to use it as sort of a roadmap or something to tell you where we are in the course. So, pardon me, from time to time we'll bounce around between these various areas, but the presence of all of these elements is what qualifies a system as a mechatronic system. So let's go through it, and then we'll come back to the pinball machine and why the pinball machine is not mechatronic. All right, let's start in the middle because that's where most people probably begin to think about mechatronics. Mechatronics is smart, right? What does it mean for it to be smart? Well, it basically means that it has a microprocessor, that it is computer controlled. Something that just has electronics, maybe a few relays, typically would not qualify, although if you put enough relays together you can make a computer that would be a fairly slow computer unless it's trying to think of the term, not mechanical but solid state relays. Nobody does that I know of, and so a microprocessor is typically a very small chip that can be used to write a program, make decisions, control a machine. So that element by itself is one thing that is needed, but not just the microprocessor, but also the logic or the control laws and the electrical drives that go with this. All this is necessary. Now, what are these things? Well, when you have a machine that has to be somewhat autonomous and has to work and make decisions, you have to somehow make an algorithm to make that system work properly. You can't expect to just make a computer and all of a sudden turn it on and it works, right? You have to write software to make that system work. And not only that, but you have to have an algorithm developed that you write the software based on to make the machine work properly. And you're going to learn quite a bit about algorithm development in this course. So that's the logic or the laws that the microprocessor follows in order to implement the mechatronic system as you design it. The drives, this is something that's a little bit different. You see, we're going to use Arduinos, but for example, we can use a computer as an example. You would never expect to plug, say, a big industrial motor directly into a computer and the computer just drive it, right? That doesn't work. The signals that come out of the computer via ports or even wireless signals are very small scale. They don't have much power. They can't drive a big motor. Even the Arduino we're going to use, yeah, it can drive really small motors, but if you have any decent sized motor, you need something to drive that motor. You need something that is sensitive to the signals that come from the microprocessor, or the microcontroller in our case, and then amplifies those signals and then can drive power to a larger motor. So this power line, that's something where we have to have some external power that the microprocessor can basically redirect. This is similar to what you do when you walk in a room and you turn on the light switch. The action of turning the light switch on doesn't require a lot of work. It's not that action that generates power to light up the lights. All you're doing is using a small mechanical signal to control a larger electrical signal. There's a lot more power going to the lights than the force times distance that it took for you to flip the switch. So the microprocessor flips the switch, but what that does is that redirects the drives to then, or directs the drive to redirect power to the motors in the way that's required. Okay, the executive mechanisms, the actuator, what's this? Well, these are the actual things that cause motion typically. So things like a motor, and there's tons of them, but a solenoid, anything that causes motion, that's what belongs over here in any actuator. So even something like a solenoid valve that then changes a pneumatic stream so that pneumatic energy flows to the cylinder, or maybe even a pneumatic motor or a hydraulic system. These are all power lines. Power is not necessarily just electrical power. There's also pneumatic power. There's hydraulic power. There's other forms of power. Let's see. Let's go to the top now. Electrical, hydraulic, and pneumatic power resources for the microprocessor, sensor, and actuators. This is really just breaking out all the different power lines, whereas this arrow down here really represents the lines themselves that connect to the mechatronic system. This talks about those power resources that are needed to make the sensors work, make the actuators work, provide power to the microprocessor. And that's why this is connected to all three. And speaking of which, we'll go on to the sensors, or the data acquisition part. Any microprocessor that's used to control a mechatronic system will need to make decisions. And what does it make decisions on? Well, not just time. There has to be sensory input. So the sensory input, things like sensing something simple like whether there's light or not in a room, sensing the pressure in on a force sensor, or I shouldn't have said that, the force on a force sensor or pressure on a sensor. All these things are sensory input. You can have things like, sensing whether or not a light beam is being interrupted. That's a photo switch. Or sensing, ultrasonically the distance to something. All of these things are sensors and belong over here in this left-hand bubble. But that data then is sent to the microprocessor, and part of the microprocessor's job, part of the algorithm, is probably some data workup of these sensors, not just taking the raw data and immediately taking that data and acting on it, right? I mean, it may act on it very quickly, but sometimes you'll see something happen on a sensor, and that means you need to go do something. Sometimes it doesn't mean anything. It doesn't mean you need to do anything at all, depending on the state of the machine or what the machine's trying to accomplish at the time. All right, now let's go down to the bottom, the support or the foundation of all this, and that's the mechanical structure and the body that holds all of this together, that has room to support the microprocessor, to physically hold it in place and protect it from the machine, protect it from the environment the machine will be in. Things that provide support structure for the mechanism so they can turn. I mean, if you've ever taken a motor and just plugged it in and it started rotating, you probably noticed the body wanted to rotate in the opposite direction. Well, the body of the motor has to be connected to something so that the output shaft turns and the motor doesn't. But also the way that the sensors are protected from the environment, the way they're mounted to the machine, all this makes a difference. So basically a system is considered mechatronic if it has all of these features. And you might go back and you think, well, wait a second, you talked about power and communication lines being connected to something, but if you think back to the Predator drone, there's nothing connected to it directly. Well, these lines are a little more general than that, right? There can be power on board. In fact, there must be power on board the Predator drone to supply power for all of the systems. Now, the communication line is obviously a wireless communication line. So don't think of this section down here as literal physical cables. It can be something that is a physical cable built into the machine and not necessarily connected to, say, the electrical grid or even an air compressor somewhere. But these are a little more general lines. All right, when I began this course, I started with the basic stamp as the microcontroller, and the reason I did that is because learning BASIC is usually a little easier than learning Arduino programming. Arduino is very C-like, and C is a powerful language, very useful. The Arduino is actually faster than the BASIC stamp, and so we've switched over to the BASIC stamp in this course, and we'll use it exclusively. It offers higher speed, better performance, and what I'm finding is that students have learned a language like Python or Java, and those things are much more closely related to C, and so students don't have such a hurdle with it. Now, that being said, I find that students still need some training in how to program the Arduino, and so the first third to half of the course does involve the Arduino heavily and learning about programming, about algorithm development. As time goes on, students may come into the course and be more familiar with these concepts, and maybe I'll be able to cut back on that a little bit. But right now, expect a lot of Arduino programming at the beginning of the class. All right, now I want you to begin brainstorming. This is a fun part of the class. Most of the students that I have in my classes are in the class and in the degree program because they're interested in the topic. They like mechanical engineering technology, or they like electrical and computer engineering technology, or they like mechatronics or robotics. And so they're in it because they're really interested in the topic. So I want to show you a few things that could be mechatronic systems we make as our final project. And when I say begin brainstorming, I just want you to start dreaming. What would you like to do as a final project? I've got an idea in the back of my mind, something that I know is mechatronic, that I think is interesting, but what would you like to do? So let's see. Oh, I should back up and talk about this. This is a game called Ice Cold Beer. It's a classic game. If you ever go to an arcade, which is getting hard to find these days, you might find one of these. It's an interesting game. Basically, there are two joysticks. There's no left and right waggle on either one of them, just up and down on each side. And what happens is you control a bar, and that bar, that bar runs along the length here, and you control each side of the bar to move it up and down. And what you're trying to do is move a ball into the correct hole. There are target holes you're trying to hit. And you want to avoid the other holes. And so you win the game by hitting the target holes in sequence. That's something that could be made mechatronic. There's many other examples. Pardon me, I'm sorry, I'm getting a call. I'll return in a moment. One project I think would be interesting would be to use these little, I'm trying to think of what they're called. They're little cheap cameras we've got. Pixie cams, that's what they're called. Use a pixie cam to look into the night sky and detect the location of the International Space Station. And the idea is then to focus a telescope on the International Space Station and track it as it moves across the sky. I think this would be a really neat project. I've got some documentation that tells how to build one of these telescopes for a fairly inexpensive price. I think we could do that. Might be able to team up with another class somewhere that's an astronomy class. I don't know. Anyway, just kind of ideas. Another example is a system that will track an instructor at the front of the class with a video camera. So you don't need somebody sitting there pointing the video camera. Instead, that's done automatically. There are systems commercially available for this, but I think it might be neat to build a system to do this. Another potential project that I think would be fun, I've always wanted to do this. This is one of those crazy ideas I've had for a long time. But if you ever heard of an Orbitron, it looks kind of like this. And an Orbitron is something you get in and you can spin many different ways. It's kind of like you become the center of a gyroscope. So it's got typically 3 rotation axes that you can rotate around about. I think it would be really cool to have what's called a space ball, that's this controller over here, mounted by the user that sits on the Orbitron, where they can control how they move. Now the space ball, the way it works, it's not a, you remember the track balls you used to be able to get, you can probably still get them these days, but you roll those kind of like a mouse to control the screen. A space ball is not like this. A space ball doesn't have the freedom to rotate 360 degrees. It has slight rotation ability along all 3 axis directions. So you can rotate it in the horizontal plane, you can rotate it in the vertical plane, and in the other horizontal plane. So anyway, the other thing you can do, it has 3 more degrees of freedom. You can push and pull in any of the 3 axes. So that would be a perfect controller, I think, for this Orbitron. But these are just my ideas. If you have some idea that you would like to pursue as a final project, talk to me about it. We'll have time in lab where we talk back and forth, and I'd love to hear your ideas. You can talk to each other as well, because we'll probably all be working on the same final project. As a matter of fact, my plan is to put 2 students together in each final project group, because a final project would be a whole lot of work for one student. Let's see, what else? Here's another project that's kind of interesting. It's a self-balancing robot. I went to, what is it? I can't remember the name. It was a machinery show basically back in 2016, a huge show at the McCormick Center in Chicago. And this one group had, wait a second, is that where I saw it? I may have seen it somewhere else. Maybe I saw this in Detroit. I don't remember now. Anyway, this robot was a very simple robot that was a self-balancing robot. And basically it had 2 wheels, and it could roll around and go wherever it wanted to go, but it was an upright, basically an inverted pendulum problem. So that's one project we could work on. A similar problem are these host robots on the right-hand side of the screen. Probably your location does the same thing we do here in New Albany, where we host prospective students every year, show them around the building. We call it Day in College. And it would be really cool to be the School of Technology and have these robots we built in-house that greet the people at the door and then turn and lead those people to the classrooms and kind of give them a robotic tour. That would be awesome. Don't know if we could do something quite that adventurous, but it's another idea for a final project. There are already people who have made self-balancing robots based on Arduino. As a matter of fact, I guess that was my last slide. As a matter of fact, in one of the times that I taught this course, we took the design offline and basically copied it and tweaked it for our own self-balancing robot. I don't have that in my office anymore. I'll put it downstairs or I'd show it to you. But that was a neat project, and even if someone has already succeeded in this area and built something, it's not as simple as just copying their design and their code and turning it on and it working. A lot of times there's a lot of tweaking that has to be done, and you learn a lot in the process. So I'm not against seeing something online and saying, hey, that's pretty cool, I'd like to do something like that, and then start using their design as a starting point. That's okay with me. So think about what project you'd like to work on, and remember, we're going to use that diagram as sort of a map as we move through the course to understand what section we're really studying. But really having all of those elements together is what makes a system mechatronic, or puts it outside the realm of mechatronics. If you have some of those pieces but not all of it, sometimes it's mechatronics, especially if you don't have a communication line. If the communication line is not something that communicates in real time, you could think of the communication line as being something, well, let me back up. It could still be a mechatronic system if the communication line is something as simple as downloading the program to the Arduino for the mechatronic system to work. That can still be mechatronic. But that's pretty much the only gray area. Everything else you have to have some type of actuator, and there needs to be precision in the mechanical components for this to be considered a mechatronic system. So I'll see you guys in lab.